Okay, yeah, hi. Welcome, everyone. I'm honored to be the first one to speak in this newly introduced dev sessions of the software working group. The idea is that this will be a quite informal thing. So I didn't prepare a fancy presentation. I'm going to share my screen, going to show you things in the browser, maybe in my development environment, depending on how it goes. And don't hesitate to ask and to interrupt and ask questions if there's anything unclear, or if you have a question about how we do things, or you want to comment on why it's a terrible idea how we do things, whatever. I'm going to have an eye on the chat as well if you want to, if you prefer to ask questions there. Otherwise, maybe Anko will also interrupt if there's something coming up, and which I don't see because, well, I'm looking on a different monitor when I'm sharing my screen. So the idea is that this will be mostly about how we develop Brine, but of course I'm going to maybe quickly introduce first Brine for those who don't know it. So it's a free open source simulator for spiking neural networks. So it's mostly targeted at biological neural networks. So it's not so much about machine learning applications, this kind of thing. Its aim is to be flexible and be useful for all kinds of models, from quite simple integrate and fire models to more complex, more like Hodgkin-Huxley type, many different ion channel models, even also for multi-compartmental models, even though that's more rather new and a bit of fringe use case until now. I don't think I'm going to talk much about it. And yeah, so it's written in the Python programming language. So if you want to use it, well, you use Python. Later on, I'm going to show you that it's using a technique called code generation. That means that even though you as a user write everything in Python, what happens behind the scenes is also that it generates code in other programming languages like C++, compiles it and runs it. But I'm going to talk about this in a bit. Maybe to just as a quick introduction, I'm going to show you one simple example, which I prepared in a, let me make this bigger, in a Jupyter notebook here. So the package is called Brine 2 because it's kind of like the second big iteration of Brine. Yeah, maybe I should have said it. So Brine has been around for quite a while. I think original development started in something like 2007 by Romain Brett and Dan Goodman originally, who are the original creators and are still involved in the development. And a couple of years later, when they decided to do this big switch to Brine 2, I became involved, I think around maybe 2012 or something, that I started becoming one of the main developers of Brine 2. Okay, so let's get started. So this in the beginning here is an import of the Brine simulator. I know many people won't like the wildcard import I'm doing here, but I'm doing it nevertheless. Keep your comments to yourself on this point for the moment. Happy to discuss anything later. So one of the features of Brine is that it has a built-in system for physical units, which I find really useful and which makes it possible to write things that are quite close to model descriptions in scientific papers, for example, so make it quite easy to go between more like biological descriptions of a model and the code. So we have these things here, which says the area is a value, it's 20,000 micrometers squared, for example, and the membrane capacitance is 1 microfarad per square centimeters, and you multiply it with the area and so on. And Brine takes care of that this all works out, or will get annoying and tell you that something is wrong if you try to add something. If you try to add a current to a voltage, it will say that's not possible. So the parameters here, so these are like kind of constants that are used in your model, and you define them as Python variables here, and they will be later used automatically by Brian. And then the core of a neural model are the equations that define your model. And these are written as differential equations, kind of as close as possible as with like this string syntax you can get to a mathematical formulation. So you write dv over dt equals and then the expression. The only thing that is a bit special, kind of Brian syntax added to the mathematical syntax, is these thing that's after the colon, and that gives the units, the physical dimensions of the variable that you defined in these lines. So the membrane potential is a variable, it's a voltage, it's in volt. These are dimensionless variables. This is a conductance and so on. And this is used then by Brian's system to check for the consistency of units, to make everything work out, basically. You then put everything together in a so-called neuron group, which here consists of 4,000 neurons, which all share the same equations, but they can have different, it doesn't need to be, of course, it doesn't need to be completely homogeneous equations. In this model descriptions here that contains the equations, you could also have neuron-specific parameters. So you could say that some time constant differs across the neurons, or that the initial values of some parameters differ, that we're going to see later. So whatever you want, you can define as part of this model. You specify this neuron group. Here we define two subgroups of neurons, excitatory and inhibitory neurons, and then we create synapses. Synapses, so this describes the synaptic model between the neurons, and there you can do a lot of stuff. Again, you can describe things with equations for plasticity and so on. I'm not going to go into much details here. In this example here, it's a very simple synaptic model. It's for each incoming presynaptic spike. The postsynaptic GE conductance, so GE is part of the equations here, will be increased by a fixed amount. Of course, this in general, the weight could be different for all synapses, the weight could be dynamic and so on. But in this simple model, it's a constant weight for all the connections. And these two lines describe the synaptic model, but not yet which neurons are connected to which other neurons. And this is done with a call connect. And this, again, you could, that could happen in very different ways. You could have rules that describes when two neurons should be connected, or it could be random. In this case, it's simply random with a probability for each pair with a probability of 0.02, so of 2% they are connected. Okay, this is a basic model setup. Then optionally, and in most models, you'd have additionally some initialization. So we set the initial values for the membrane potential and the excitatory and inhibitory conductance. And this could be some fixed values. In this case, these are expressions, so things that will be evaluated by Brian. And they refer to these functions that have the same names as the NumPy functions for random numbers. So this will use normally distributed random numbers to introduce to initialize these values randomly. Okay, then that's everything together to describe the model. Then for most models, you're also interested in how the model evolves over time. And so you add some monitors that record some of the variables during the simulation. In this example, there's a state monitor that records a state variable of the model, in this case, the membrane potential. And here we don't record it for all the models, but just for 3 of them, the ones with the indices 1, 10, and 100, whatever. I mean, these neurons are all random anyway. We could have recorded the first 3, would have been exactly the same. And then we run it. And well, this will then run the model, and report text just means we get some output. And if I do this, what we see is so it will actually output something as soon as it starts actually recording to the model. And as you're seeing, it's not outputting anything yet, which looks a bit odd. So there seems to be a long delay until it actually starts the simulation. And the reason for that is that it's behind the scenes, it's doing code generation. So what it's doing by default, is it actually doing something? Yeah, it's doing something. By default, it uses Scyther. So what it first does is it takes your model description, it applies numerical integration algorithm. In this case, it's the exponential Euler algorithm, because applies this to the equations, generates Scyther code from it. The Scyther code will be transformed via Scyther to C++. The C++ code will be compiled, and then it finally gets executed. So there can be quite a significant delay. Also, I'm running this on a laptop that is not very powerful. And then the simulation takes a certain amount of time. This code will be cached. So if you run exactly the same simulation again, it will go much faster. But still, for simple model, this code generation adds quite a bit of overhead. So Brian has several different modes in which it can do the code generation, and I'm going to talk about this a bit more when I'm going to when I'm talking a bit more about the developing side. So what we're doing here is the so-called runtime code generation mode. And what it means is, maybe let me show you one figure from, is this helpful or not? Yeah, maybe. Let me I'm going to show you one figure from one of our paper about Brian. So what happens is it's a two-step procedure. So what happens is, first of all, the model equations that you define. So in my example, weren't the same, were a bit more complicated equations. This here is more like an integrate and fire model with an adaptive current or something. So these will be first transformed into what we call abstract code, which is some kind of intermediate pseudocode in a way. Which is just because these are differential equations, you have to convert them into a step procedure, kind of like difference equations. So something that you can update from time step to time step with some numerical integration algorithm. In this case, it's like a simple forward Euler integration. And then this gets transformed into C++ code, for example, or Scyther code. And the way it is done is that there's basically some fixed template code. In this example, there would be like the loop for would be like a loop over all the neurons, and then there's a little bit that is really specific to your model, and that gets kind of inserted into this template. And the abstract code is still Python strings. So everything there is still on the level of Python, basically. And so for each component of your model, so I'm going back to this example. So each component of the model will be one little code module. So we call them code objects internally. So there will be one code object that is responsible for numerically integration the equations. There will be another code object for checking whether the threshold condition is fulfilled, one other code object responsible for propagating spikes, one other for resetting after spikes happen, and so on. These are all individual little objects. And we call this runtime mode because these little objects will be used at runtime from a general Python loop. So so the Python loop schedules all these objects. So first, during a time step, it's basically a loop over time step. And within each time step, it says, okay, now execute this little object that updates the equations, then execute this that checks whether the threshold condition is fulfilled, then do this, the module that propagates the spikes, and then do this thing to reset, for example. But all is still handled in a way by Python, which has the advantage that you can interact with it from Python. So a feature that Brian has, and I'm not showing it in this example here, is you can intermingle your generated code with manually written arbitrary Python code, which can be useful to do whatever, basically. So it could be you want some real-time visualization of what is going on during your simulation, for example, or you could connect your simulation to, I don't know, input from your webcam or whatever. Whatever you can do in Python, you can write in a Python function, and you can tell Brian basically to inject this into the loop and execute it, for example, every time step or every 100 time steps if it's something that shouldn't happen so often. So it's very flexible in that regard. But of course, this comes at a cost, because there's a certain overhead of going to call a little C thing, go into Python again. So it's not the most efficient way of executing things. And that doesn't matter much. It's if each of these code objects does a lot of work. So for example, if you have a big network and your equations are very complicated, then, well, the object to update the, to do the numerical integration step is quite complex. So it will do a lot of work. So this little overhead that is more or less a constant time will not matter much. But if you have rather simple elements and you have many time steps, which, for example, would happen if you're interested in synaptic plasticity, but your neural model is very simple, for example, then this mode can become a bit inefficient. And so not only for this reason, but in particular for this reason, we have another mode, which is called the Standalone Mode, which takes all the code that you have written, transforms it into C++ code, but also writes the main simulation loop in C++. So you end up with a big, well, basically a directory of code, which all gets compiled into a single binary. And at the point of the run, basically it runs the full binary. So the disadvantage is, of course, well, you cannot just inject Python code somewhere in the middle, because, well, it just runs this binary and waits for it to end. But of course, it can run faster. And the way you do this, well, the syntax it's not the greatest. I hope at some point we're going to change it. But in Brian lingo, we call this the runtime mode runs on the runtime device, and the standalone code runs on the CPP standalone device. So you add this little set device here in the beginning, but basically all the rest can stay the same. And at the point of the run, what it now will do is basically generate this bunch of C++ file, compiles them, run them, and in the end we'll get the result. Actually, I never showed that we actually had results. Well, but I'm going to show this in a minute. One thing that is a bit odd when you run this in a Jupyter notebook is that it's actually now the C++ code that prints out the status report to standard out, and this unfortunately never ends up in the Jupyter notebook. So I'm seeing it on my terminal where I started the the Jupyter notebook, but you are not seeing it now. But it finished. It ran the simulation, and actually now let me plot something to show that it actually simulated something. So, well, we have neurons that spiked. Maybe to give you an idea of this standalone mode, what it does behind the scene, because after all, it's supposed to be a dev session. I can just show you, whoop, here. So what it does, it creates a folder with a not very useful name, output, but you can change the name of this. And you see that's a folder full of files. So in particular here, there's a main.cpp file, which pulls everything together and gets compiled into a file main. So this file main is basically the binary that gets run when you run the actual simulation. And that's why it's called standalone mode. So this folder is completely standalone. So you could take this away, forget about Brian. You have your C++ code that makes your model run. You could take it onto a machine that is able to run C++ but doesn't have Python, but doesn't have Brian installed. You could compile it, run it on that machine, and it would work. So how do you get the results back from this? Because I mean, in the end, in Python, I plotted my results. This communication happens in a very straightforward way. It happens over disk, basically. What this binary does is, maybe let me show you. It should be in this nice and long file. In the end, yeah, there's this C++ file that gets pulled in from main.cpp. It has a long function called write arrays, which writes all the simulation results to disk, basically. All the variables that were simulated or recorded got written to disk. I mean, this is automatically generated code, so it doesn't look very nice, but it's somewhat readable. And so these files end up in a folder called results. And here we have basically, for each of the variables in a model, we have one file that have the name of the group to which they belong and the name of the variable, and then a very ugly looking unique identifier number. And the only reason for this number is because Windows file systems don't make a distinction for the case of variables. And we once ran into the problem that we had two variables that were capital case V and capital and minor case V, and under Linux that's fine, but under Windows they'd be the same file, and so we just added a unique identifier to all the file names. It's a kind of like a brute force solution, but it works. And basically in my Python code, so when I'm plotting the variables here, I'm asking for the V variable recorded by the state monitor. What kind of magically happens behind the scenes is that Brian knows that we are in a standalone simulation mode, and it will read the file containing the information about the recorded membrane potential, and then it's available on Brian. And and from then on, it's kind of the same as what would happen during runtime mode, where you'd actually have this Python variable in memory. Okay. So that's the standalone mode and runtime mode. And maybe while I was talking about the runtime mode, so you could, whoops, that's not what I wanted to do. So you could explicitly ask for the runtime mode, but normally you don't have to do this because it's a standard mode. But maybe one thing that can be useful when you're trying out, when you're trying out things, is basically to switch off the default code generation for Scyther that goes to C++, compiles everything and so on, and do code generation for NumPy using NumPy. So which basically means generate Python code, which is much faster because it doesn't have to do, I mean, it's much faster for getting things started because it doesn't have to generate Scyther code, compile it, and so on. And actually, let me start this and hopefully runs. And maybe you saw the difference. It basically immediately starts the actual simulation. The simulation then will be a bit slower than what it has been with Scyther, so on the order of twice as slow normally. But it depends what you're doing. So especially when we're doing things for teaching, for example, or very simple models, you don't want to wait 5 seconds for the compilation to finish to then have your simulation and finish in 100 milliseconds instead of 200 milliseconds. Maybe it would be smarter in this case to switch off the code generation and just use Python. But just that's a thing also for trying out things that can be useful. Okay, there was a very basic introduction. Maybe I lost my chat window, but I think that there was maybe a question. I found my chat window. Can the abstract code be accessed? Indeed, it can, even though it's not exposed in a super nice way. So there are these code objects, and these in the end, each of these code objects stores the abstract code, and then also the generated code. And for example, this will not be beautiful, but for example, for this neuron group with a couple of equations that will be integrated according to the exponential Euler algorithm, you could find there's a state updater object, and attached to this code state updater object, there's the code object, and this, no, actually the code object will have the actual code, but if you're only interested in the abstract code, this will be here in an attribute abstract code, and this, whoa, I should maybe print it to make it, well, this doesn't look super readable because it's the exponential Euler algorithm applied to these equations, but it's what it actually does when it gets executed. I mean, actually, so this is one step. Then the code will be generated, and in between the two, there's an additional step that I didn't talk about. It's an optimization step. Because, for example, in this case, we are simulating these equations for 4,000 neurons. So the basic approach is there's a for loop over the 4,000 neurons. And for each of these equations, we are evaluating these statements. But there are many parts of these statements that are the same for all neurons. So, for example, in this case, if the synaptic time constant for the synapses is the same, then this expression, the exponential of the 1 minus times dt over tau e, is the same for all the neurons. And so we pull this out of the loop. And so if you look at the actual generated code, it will look quite different from this here, because it pulled a lot of expressions out of the loop that don't have to be evaluated for each neuron, but can be evaluated once. And there's some other optimizations. So for example, if there's some terms that are multiplied with 0, we pull them out, or we throw them away, even though some of these are probably the compiler would also do for us, but it seems to be helpful to do this a bit. Sorry, I was a bit distracted by Thomas' question. The array code and scalar code in Brian speak. Yes, so it's called scalar code and vector code in Brian speak. Maybe in a few moments, I'm going to show a bit how this looks in the generated code, and this might be clearer. Yeah, so we do a distinction between what we call scalar code, something that needs to be executed once per time step, but not once per neuron, and vector code, which is something that has to be executed once per neuron, or if you're using NumPy in a kind of like an array vector way. Okay, so there was, I mean, I mixed in a few things about development or how things are going in behind the scenes, but in general it was more interaction to Brian itself. So maybe I'm going to go a bit more to the development side. Maybe before I do this, just for if you're more on the user side, things to look at if you're interested more to learn about Brian. So there's briansimulator.org, the main web page where you find mostly links to everything that could be interesting. One of the main places now to go if you have questions or if you want to discuss anything is our discussion forum, brian.discourse.group, where you can discuss things, especially in the support category, where if you have any questions, there's actually a new support question that I didn't see yet. So yeah, normally someone will answer quite quickly. And there's also, we have a chat on gitter.im. So gitter.im, actually I can't see my URLs because I have this Zoom share bar, but I think it's gitter.im/brianteam/brian2, which is more of maybe if you're more of a quick question where it might be useful to have a back and forth, you could also use that one. And finally, the place where all the magic happens for the development, and of course also if you encounter a bug, maybe ignore we have a problem with building your account banner. That's because I need to update my GitHub doesn't believe I'm an academic right now. That's a minor issue. So the main development happens on github.com/Brian team/Brian2. So this is really everything around development happens there. So we use this for, of course, the actual source code, like, I don't know, like 99% of all open source projects nowadays. The main development Git repository is on GitHub, so you can clone it from there in the usual way. So I'm not going to talk much about that because I think that's there's nothing that is much Brian specific there. Then we use it, of course, as an issue tracker. So the issues either if you find a bug in Brian, or if you if you have a feature request or whatever. I mean, we use this a lot for all kinds of discussion, and pull requests if you want to contribute directly to the Brian, but I'm going to maybe come to this a bit later. There's James who asks, how come you use Gitter and Discourse? Well, because why not? It's not exactly the same thing. So Gitter is really like chat, so it's more interactive in a way, and Discourse is more the classical discussion forum. The Gitter thing is not used that much, to be honest. So I'd say the main point for discussion nowadays is the Discourse forum, but we didn't introduce the Discourse forum until I don't know, half a year ago or something. So it's still relatively fresh, and we have the Gitter chat. We had it around for a while. Okay. So let's talk about a bit about how things are organized on GitHub, and maybe maybe one big thing I didn't mention yet, but which is of course very important, and I don't have it open at a, do I? No, I don't. Which I didn't mention yet, but is of course very important, is the documentation page at brian2.readthedocs.org. Yeah, I'm seeing Rory's message, and I'm coming to something like this maybe a bit later. Maybe just a few things about the documentation. So the documentation is, of course, very important, and we put quite a lot of work into it, even though there are many shortcomings. But that would also be great places to contribute, of course. Maybe just quickly, if you're a beginner, I'd strongly suggest you to start looking at one of the tutorials. The tutorials are written as Jupyter notebooks, but you can hear they're directly included as a kind of like in a kind of read-only version in the documentation. But you also you can also download them as actual Jupyter notebooks that you can run on your own machine. And then there's also this MyBinder infrastructure where you can actually run them directly in your browser. So this will launch up a cloud instance of this Jupyter notebook, and you can directly try out things there. It will take a while, blah, blah, and it's not always available, but there it started up quite quickly. And so you can try out Brine basically without having it installed on your own machine. So the tutorials are very important, and the same thing for the examples. So it comes with a number of examples, like the one actually that I used as an example. And you see, you can find them here in the documentation, and you can also launch them on this binder if you want to try out an example without actually installing anything. So maybe for the documentation, one small feature that can be interesting, especially if you're interested in developing it, is if you go to brian2.readthedocs.org or .io, by default it sends you to the stable version of the documentation, which is the documentation of the latest released version. But if you click on this, you can also go to the documentation for a specific release, which might be less interesting. It's mostly to have stable pointers to old. If you have links to a specific versions, they will stay around. But maybe more interesting is going to latest, which, as the name suggests, goes to the latest version of the documentation, which would be the development version that is built from current GitHub, from the current GitHub master branch. Okay, so let's talk a bit about development. So that's the documentation. It's on Read the Docs. So this will be built automatically. It will be built automatically on Read the Docs. So for that, we configured Read the Docs to do this. The documentation is in this docs Sphinx folder because it uses the Sphinx package, which is the standard package for making documentation available in Python, I'd say. There's some stuff here. Maybe go to user. So documentation is written as restructured text files. So if you wanted to change something in the documentation, that's where would do it. Actually, you can do this. It's the lowest threshold entry to contribute to Brian would be actually to fix some error or add something to the documentation, which you can even do directly on GitHub. So if I find something that is wrong here in the equations documentation, I could click on this little edit this file button and well, add it to this text directly here, can preview my changes and see whether everything still looks good. And then at the end here, actually do a commit. And for most of you wouldn't be allowed to commit this directly to the master branch, but you'd only have this option to create a new branch for this commit and automatically start a pull request to to contribute this change to the documentation. And then some of us would review this proposition, and we would then say yes or no and accept this change to the documentation. So that would be kind of the least threshold entry. Yeah, it's maybe a bit too specific, but maybe the way the examples and the tutorials build is a bit more complex, because it does this thing where it from Jupyter Notebook tutorial, it creates this version that will be included in the documentation itself, but there's also the notebook on the side, and will integrate this into MyBinder. So if you wanted to write a new tutorial, for example, you wouldn't have to care much about that. You would just have to add it into this folder tutorials here and write a new Jupyter Notebook, and then our infrastructure would take care of the rest. So there would be a build. So we have a script here in dev tools docs, I think, which is called build tutorials, which would take care of doing all stuff around it. But just writing a new tutorial would be a very welcome addition, even though I don't think anyone would do that. Maybe more realistic is writing a new example, because this literally just means having a new Python file and putting this into our examples folder. So that would be like the user contribution. And then our documentation pipeline would take care of integrating this into our documentation. There's one extra step one had to do manual, but that could be us. That is, again, running a script from our dev folder, which is, I don't quite remember, generate examples or something. No, run examples, I think. Run examples, yeah. Which is an additional step, because this will run actually the examples and create figures. And this, we don't do this as part of our upload process to read the docs, because for some examples, it takes a while to actually run these examples. And also there's something which is a bit more complex, but you don't have to care about much. We see here in the docs things, there's this folder resources is a special thing called a Git submodule. So the stuff that is in this folder is actually not part of our repository, but it's in a separate repository. That's simply because these images, they take up quite a lot of space. And if you do a new version of images, well, Git isn't very good at compressing the differences between these images. So this quickly adds up, it becomes quite big, and we don't want everyone who clones our main repository to automatically also have to download all the history of all these images in the examples and so on. So this is separated, and then with this Git submodule thing, all gets integrated again. I mean, it's something I could talk about in more detail, but maybe that's not the most relevant for most people. So just to kind of summarize, so the kind of contributions on the documentation level would be either in the docs things directory, edit or add restructured text files. For the tutorials, you'd have to write or edit one of these Jupyter notebooks. And for the examples, it would be adding .py files to the examples folders. And because I'm seeing a question, the examples will be, how examples will be shown. They will be shown like this in the example. Or you mean if you edit an example and you want to see how they are shown yourself? Yes. If you want to do it yourself, so you have to rebuild the the examples on your local machine. And for that, there are scripts. So in Tools, Docs, you can run this script build HTML Brian 2, which is maybe not the greatest name. It's in DevTools Docs, and if you run this script on your own machine, so you have to have Sphinx installed, then it will generate the documentation on your own machine, and then you will have a folder that is in parallel to this docs Sphinx folder, a folder that would just be called docs. And this is where there are then the HTML files that you can open on your own machine. We hopefully, and that's actually a good point, the documentation is not only for users, but also for developers. So there's a section here which is called Developer's Guide. And if you go to this, then nothing happens. Then you find, for example, a part about documentation. And it talks a bit mostly about documenting, how to document classes with doc strings. And maybe it doesn't talk much about how to build the documentation on your local machine, but it should, no, here it mentioned the script that I mentioned. So it talks about it a bit. And in general, so this is a place where we also talk a bit about how some coding conventions, some things that if you want to contribute something to the actual source code, so not only to the documentation, this is certainly a place where you should have a look, even though I guess potentially some places might be a bit outdated, but in general there should be quite a lot of useful information in there. And maybe that leads me to one big thing. If you wanted to contribute, which of course would be great, and so on, or even if you find a bug and a bug that we didn't find, one very important thing, of course, is tests. And I think now every serious software project has extensive test suites for testing all kind of stuff. And in Brian, these are in the package called tests, surprisingly. And so there are tests for all kind of stuff. So let's go, for example, to test neuron group. And yeah, this is what a test can look like, for example. So tests, we're using the PyTest framework, like I guess most, many Python projects now. And tests, to write a new test is very simple. You have to add a new function that is called test something and add this to one of the files called test something. That's it, and you wrote a test. So you could also, if you add a very new feature, you could create a new file, test something, but most of the times, if you want to write a new test for the neuron group, you'd put it in test neuron group, for example. The only thing that is essential is that the function is called test something, okay? Then, as I explained in the beginning, and that's a bit special about Brian, and that makes the whole testing process a bit more complicated, is all our code generation machinery. So that same code could be run with this NumPy code generation, with Scyther code generation, with the standalone mode. So this is where things can get a bit complicated. And this is where we use these PyTest markers. And this is explained in the developer documentation a bit, what kind of markers we need. So we have some tests that are independent of the code generation process. So that is something that very basic syntax, for example, you use the neuron group in a way that is wrong. So then you would mark it as a code generation independent test. Then there are other, let me find a test which doesn't have any annotation. well, I don't have anyone here, but there's one that is, yeah, it's a different one. That's one that tests something that is actually using the code generation. But not all of these tests will work with a standalone mode, because the standalone mode is a bit special. You cannot interleave things with Python. You cannot access things before things have actually been simulated and so on. So not all codes are compatible. So those that are compatible, you have to mark them like this. And there are other annotations, but that goes a bit too much into details. So these tests you can then run on your own machine. And because we have these different code generation targets, it's a bit more complex than just using the standard PyTest mechanism to run them. What I'd personally do on my machine, I use one of these scripts that we have prepared for that. So they are all in dev tools. And there's, for example, one script that is called run tests that basically runs all the tests. All the tests in standalone mode, in not standalone mode. And then there's another one that only runs the tests in standalone mode, and then there are more variants. You can also, there are a bit more specific ones where you only run Scyther tests, for example, and only NumPy tests and so on. So there are various things. That's more when you develop on your own machine. But when you do commits and you push them to the server, I mean, for us, if we put them to the main repository, that will be automatic. If you put it to your fork, it will only run the test suite if you open a pull request. But then they will run automatic. And in our case, currently, they will then run on the Microsoft Azure infrastructure. And then there's where things get, again, complicated, because we do all these code generations and it's C++ code. And let me show you an example here. We have to run the codes on Python and on Windows and on OS X. So this gets, so here there are like 17 different test suites running things on Python 3.6 up to Python 3.9 and on Linux and Windows and OS X. So this takes, unfortunately, 4 ages, which is a big disadvantage of our current test suite. But on the other hand, it's quite thorough. There was a question, how long does it take for a normal machine? Well, it depends on what kind of tests you run. So we have also a subset of tests that we don't by default run, which are called long tests. So you have to activate a separate switch to run them. And then it also depends on whether you already run the test suite, because I already, as I said before, like the Scyther code generation, for example, it caches compiled code. So if you run exactly the same test again later, and it generated the same code, so there's no reason to regenerate it, then it will be much quicker. But on your own machine, a full run of the test suite without the standalone, well, it runs on the order of several minutes. Maybe the full thing might be something on the order of 10 minutes, but it really depends on what you run. So there are a lot of options that you can do. On the test servers, a full run of the test suite for one Python version and so on, it runs also on the order of tens of minutes maybe. So it's a problem. So to run the full test suite on the servers, because it runs things in parallel, but not, I think, maximally like 10 things on parallel. It takes like an hour or 1.5 hours or something until the test suite run through completely, which is a bit of a shame. But on the other hand, it also means you kind of step back a bit. You don't merge things prematurely. You wait. You let it mature overnight, and next day you see whether all actually ran through. And yeah, that's the way it is. There was a question why we have both standalone and Scyther mode. It makes it harder to maintain. It does actually make it harder to maintain. But the thing, there's a difference between the Scyther mode and the standalone mode, is that the Scyther mode is still this runtime mode where things can, you can mix and match things with Python basically. So you can have, during a single simulation time step, things using these compiled Scyther code, but other things are executed in Python, like some custom written, say, real-time visualization code that you added in Python. And that works for the Scyther, but it cannot work with a standalone mode, because this is really like you run the full simulation in C++. We have other ways to extend C++ code, so you can have your own handwritten C++ code that you inject into the generated standalone code. But that's, of course, it's more difficult than just writing a little Python function that does something. And I mean, you don't, I wouldn't recommend using this for some real-time visualization code, for example. That would be more complicated. But in the long run, what we'd like to do would actually be to get rid of this Scyther part and just generate C++ directly and share this bit between the standalone and the runtime, and yeah, get rid of the intermediate Scyther stage, which also costs a long, is very costly in terms of the compilation time. Because this, I mean, Scyther is great in general, especially for, you can have start with Python code, then make it more and more Scyther, and it all works magically, and it's quite nice. But for our use case, we already generate like pure Scyther type annotated code and so on. And the C++ code that Scyther generates from this code, it's huge. So for our quite simple stuff that in standalone mode are like 100 lines of C++ code, what Scyther generates is like 1,000 lines of C++ code. And that takes a while to compilate and so on. So it's, yeah. Okay, there's a question like a huge directory of examples which we keep out of our GitHub repo. Yeah, in our case, maybe we don't have as many examples, but so all our examples are here in these, are included in our main repository. What we don't include is the images that are generated when you run them. So they are outsourced into this, it's a separate repository called Brian2doc resources, which has the example images, for example. But that's mostly for size reasons, and we don't want to. Yeah, link repos. So it's called a Git submodule, and there's some arcane Git magic to do, but then it works. Basically, I mean, in a way, it's, I mean, under the hood, what Git does is not that complicated. Basically, what it does is, in this folder, which you initialize as a Git submodule, it basically just notes down the name of another repository and the Git commit it refers to. And then basically you have these Git submodule commands that can put everything up to date. And yeah, but there's some things to take care of. I mean, you shouldn't, yeah, things can get out of things in weird ways and so on. But in our use case, it works fine. And yeah, they're good references to how to use it, but you shouldn't get too fancy with it. Basically, use it in a simple way, and all will work fine. But as always, like Git, it can be things can go wrong in terrible ways. Then you just delete and start anew. Okay. Yeah, maybe I wanted to. We took already much more time than I thought this would take, but maybe one thing that I wanted to show of the actual Brian code. So I mean, I'm not going much through the Brian repository. I mean, most of the code is kind of like I don't know, standard Python code that you expect. So I don't know, there's a package called groups, and in this there's a module called neuron group, and this is where you find the core definition of the neuron group. So there will be somewhere down here there will be a class neuron group, which is a group of neurons, and then, well, there's Python code. Okay, so far so good. But what is quite specific to Brian is everything that is related to code generation. So earlier I was talking about these templates, and maybe this is one thing I can quickly show. So for example, as I said before, this numerical code integration step, you have some user-defined model. This is transformed with this numerical integration algorithm. Then it's transformed into, say, Python or C++ code. And then this code is put into a certain template. So for example, what is interesting, most of these templates are really quite straightforward. So let's, for example, look at this reset template. So it's the thing that is evoked to execute the reset statement in integrate and fire models. So for all the neurons that spiked. And basically what it does here is has a loop over all the neurons that spiked. And then it executes what we call vector code. So that's the code that is specific to each neuron. And before, there's a kind of placeholder for the scalar code. So these templates are where our model specific bits that gets put in. And as Thomas correctly remarks, this is done via Ginger 2, which is a templating tool that is also used a lot for like web stuff. And so you have all these templates, both for the runtime mode and also for things like the standalone mode. Yeah, there's so the same thing here. What is added for the standalone mode is something that I didn't talk about. There's some bits and pieces because in standalone mode we support OpenMP for parallelization over processor cores. So there's some bits around it that tries to some trivial loops that try to parallelize them over processor cores. So this is the core infrastructure, and that as soon as you touch at the whole code generation things, unfortunately, things can get complicated quite quickly. So if you're interested in really contributing core features like this, you really have to invest some time to look at our developer documentation a bit, go through some examples by hand, see what the generated code looks like. This is unfortunately quite complex, but on the good side, it's quite complex also for a reason, because we wanted this system, which we call the device system, to be quite modular. Because this is a standalone mode here, it's used for our C++ code generation. But the same system is, for example, used for the Brian to Gen, what we call also device, which generates codes for the Gen simulator, which Thomas and Jamie are developing. So this means we can use our same Brian code. You just add one line to the beginning that says instead of set device CPP standalone, you say set device Gen, and then all the code generation magic happens, and things will then run on the GPU, for example. With some restrictions, not all the features are supported, but in general, this works. Yeah, that was one thing I wanted to say. What more? Yeah, but the general contribution development process, I didn't talk too much about how we do things. I mean, the way it basically goes is, I'd say, like most projects that are on GitHub nowadays. So if you want to add a new feature, either as an external contributor or us as the main developers, what you do is you create a new branch for your feature, starting off the master branch. You start implementing your feature, and then you create a pull request. And then you end up here at this pull request stage. Nowadays, GitHub has this new feature that you can mark a pull request as a draft pull request when it's not completely finished yet. And then, no, what is a good, these are all very old, and there's some, so this was a pull request that is still ongoing, where we have a very long discussion, but this is the way it works. I mean, you propose something, and then a discussion starts, and people have opinions, and we, well, discuss things. And normally, usually we use this, maybe let's have a look at one closed pull request. What is yeah, I don't know. This one, for example, which was a real bug. Then there's this feature normally that one of the main developers has to approve this pull request. So what we try to do is, that's not, I mean, for external contribution, it's clear that one of the main developers will have a look at it. But also when we internally, when we develop new features, what we normally do is, if I contribute a feature, typically, for example, then Goodman will have a look at my contribution and will kind of approve it. Or the other way, if he adds something, then I would typically, for example, approve it. So we try that there's at least another pair of eyes that had a look at it, in addition, of course, to the test suite. So there's basically no reason. I mean, we never merge anything into master where the test suite fails, except for some exceptional circumstances that we had sometimes where there was basically problems on the test server side, that our tests under OS X were failing for some weird library issue on the test server or something. So sometimes then we, for a certain time, we merged things or deactivated some of the tests in the test suite just to make the test suite pass. But in general, it's mandatory that the test suite passes before things gets merged into the main master. So the idea is that you could at any time basically use the current development version of Brian from master, use it, and it should work. And then from time to time, so about every couple of months, then we do a new release that gets uploaded in the usual way to PyPy, and we now have these packages on Conda Forge as well, so that you can then install in the usual ways. But in general, our aim is really that the master branch is always usable as it is. So we don't really do development in the master branch. The master branch is always just takes the emerges from external feature branches and pull requests. The only things we ever commit directly to the master branches, like small fixes to the documentation or the README or something related to the, maybe to the test suite infrastructure, things like that. But in general, everything passes by pull requests and feature branches. Okay. Yeah, I think for the moment, that's, I mentioned a lot of things. I probably forgot a lot of things as well. But maybe if there are any specific questions or about any of the tools we're using, or I mean, I kind of scratched the surface. I didn't go into much details how we set up, I don't know, our testing pipelines or the documentation or whatever. So if there are any specific questions, I'm of course happy to answer them. Yeah, there was a question earlier, I think, about any follow-up question. In which system is to use a standalone mode? Yeah, about the standalone mode, in general, if you can use it, so if you don't run in the restrictions, then I'd say in general it's always beneficial, and it doesn't cost you much. I mean, if your model is already in a state where you can use it because you don't need Python interaction during a run, and you don't access things in ways where you don't, then yeah, there's no reason not to use it. It will not necessarily be much faster. It really depends on your network, but there's no disadvantage, no real disadvantage to using it, basically. Right, yeah, Thomas. No, it is, the code generation pipeline is complicated, and actually one of the main things that we want to do from the developer side, but unfortunately is one of the areas where it's really hard for external contributors to actually help, is to refactor this code generation pipeline and make it more straightforward and clearer and easier to contribute to as well. But that's kind of, I mean, it's a thing on our shoulders that we have to attack, and then hopefully it will be clearer to others and also easier to contribute. But unfortunately, as these things go, for now, yeah, it would be great if other people could help us with that, but it's, yeah, it's too complicated for, I mean, it's, yeah, it's a bit of a mess. And I mean, the developer documentation should certainly help, but the pipeline jumps to many hoops, and there are many reasons for why things are why they are the way they are, but some of them are historical and others are many corner cases that we have to take care of. But it's one of our major, and I think there was a question about what is on the list. There are few, we didn't use this feature much yet, but GitHub now has this projects feature, which we want to use in the feature a bit, maybe to structure. And one of them is refactor code generation. And another one is what is called encapsulation mode. Without going into too much detail, but one of the main thing that we want to improve in the future is something, especially with standalone mode, is not very straightforward currently, is a workflow where you have basically the same simulation that you want to run several times, but with different parameters, for example, to do explorations. And of course, you can do this currently, but what it basically will do is it will regenerate and recompile code a lot of times unnecessarily. And there are some kind of workarounds which you can find if you search for it in the discussion forum, for example, or mentioned in some of the issues and so on. but they are not very user-friendly. I mean, you have to know a bit about the code generation internals, how to avoid these recompilations, and it's a bit ugly, and we would like to make this more straightforward and more clearly exposed to the user. Ginger, not ninja. I'm not sure what this comment is referring to, but yes, Ginger.
It's me not being able to spell. Sorry, Marcel.
Sorry.
I did spell ninja earlier. It's complete
ninja
nonsense.
template. All right. Okay. Yeah. No, yeah. Yeah. Ginger templates. Exactly. Okay. Are there any other questions or comments? Maybe someone like why on earth do you do things like this? You should use X, not Y. I don't know. Microsoft Azure. How
I think your websites in particular look fantastic. So I'm jealous, and you set a high bar. Yeah, no, everything looks very impressive.
I could talk about our amazing system for the website, because it's all markdown files, and yeah, we actually did a rewrite of the our website was super ugly for a long time, and last year we took some time to actually remake it.
Yeah, it looks great. And yeah, I like the separating documentation website from the main website. I think we may do that as well. So yeah, this has been very useful. And I had a bunch of questions, but you answered them all during the presentation. So thanks a lot, Marcel.
Great. Yeah. Yeah, I mean, this separation of the main documentation from the website was actually, it's half planned. I mean, basically was because we started having the documentation using Sphinx for it, and then this read the docs thing came up, which really simplified our lives for setting up and keeping the website up to date. So we had this separate, and then we redid the web page. Nowadays, also with GitHub pages and GitHub Actions, you can do this updating of the website, of the documentation on a website quite conveniently. So maybe now we wouldn't have separated it, but yeah, I mean, read the docs works great, so I'm happy with it.
Yeah, I think it's generally a nice idea to have a different, let's call it flashy website, which is sort of to sell your tool to the audience. And then documentation, of course, will be slightly more technical with more tutorials. And yeah, so we try and separate those two also as much as possible. I mean, they're both markdown or whatever, but we just try to have them in different places. And link.
Yeah, it's true that they have slightly different purposes. So, so our main website is also, I mean, there's some information on it, but mostly it's also like pulling all the things together. I mean, it's links to the documentation, to the discussion forum, to stuff. I mean, we started writing some like articles, kind of blog post things on it.
Yeah.
But it's, I mean, the main point is, I mean, you maybe Googling, for example, you end up on it, and then it points you to all the other things.
Right? Yeah. There's one last question, Marcel, that's just come in. Do you want to answer?
Yeah, I see it. Event-driven simulation supported. No. So it's all about clock-driven simulation as such. And well, the main reason is, one reason is clock-driven simulation is simpler, but also more general. So the thing is, event-driven simulation normally is great for models where you can calculate exactly the trajectory of your membrane potential between two events, between two spikes normally that come in. So mostly very simple neural models where you basically have an analytic solution of how your membrane potential develops in between two spikes. Brian aims to be very general. You can have arbitrary and very complex models. And for most of these models, like the Hodgkin-Huxley model that I showed earlier, you cannot do this exact calculation. So you have to do some numerical calculation in between spikes. And the second reason is also when you have networks and you kind of go up to non-trivial network sizes, what you typically have, you have many spikes arriving at a neuron. And what can happen quickly is that basically you have at least one spike arriving every time step, or at least one spike every few time steps. And then, well, the advantage of your event-driven simulation goes away anyway. So we discussed it at some point, but I think in one of the papers written by Dan and Romain, they have some kind of like formal argument why event-driven simulation is not that interesting in the end, after all. But it also depends on what you want to do. I mean, if you have only one very specific neural model, and for that it's appropriate, you can do very interesting stuff with event-driven simulation. But because Brian aims to be general, we clearly opted for clock-driven simulation, which applies to each and any neural model, whereas event-driven is more specific. Right. Yeah. Sorry. Yeah. It also depends a bit on what you call event-driven. So we have a bit of event-driven in it, because for synaptic models. So first of all, the synapses itself are driven by events, and also what you can have quite often, for example, for spike timing dependent plasticity models, you have something very simple like a trace variable, which you have for each of the synapses, but it has a very simple mathematical form, like just an exponential decay. And for these, we have a mechanism to support event-driven simulation for those, because it would be very costly for each of the synapses to have a simple trace variable which only exponentially decays, to update this for each of the synapses at every time step. So for these, Brian basically does the analytical solution of the equations and plugs them into the statements that get executed for a spike that arrives. So there's a bit of event-driven also in Brian, but not on the level of the neural equation, only on the level of the synaptic equations. But where it is the most relevant, actually, because typically you have many more synapses than neurons in a network model, right? Okay. No, I don't see any more questions in the chat. You have exact solutions for simple neurons. Yes, we do. Brian's numerical integration mechanism can, for simple neural models which have an analytical solutions, you can, as in numerical integration models, you can ask for the method called exact, which uses SymPy, so the symbolic mathematics toolbox for Python, to actually calculate the exact solution. Well, what we don't do is we don't have a mechanism to use this to only update the membrane potential of a neuron when a new spike arrives, for example, which we in principle could do. And also some simulators have, for some neuron models, a mechanism to have, for example, exact spike times. So spike time to calculate when a neuron would cross a threshold even within a time step. We don't do this. In principle, there would be a way to, but no. If someone is interested in adding this to Brian, let's open an issue about it and talk about it. It's technically, it's a bit complicated, but we don't do this. In Brian, everything is clock driven, so spikes are aligned to the grid of the simulation. But on the other hand, we are a bit more flexible than most other simulators. For example, what you can do in Brian is you could, for example, have two separate neuron groups, one with a very simple neural model, one with a very complex neural model. And the complex neural model could use a finer time step for its simulation, for example, because that's necessary for numerical reasons. So we can have different time steps for different parts of the simulation. Okay. There are no more other questions. This was a solid 1.5 hours.
Yeah.
maybe on the longish side for these sessions.
No, I think it went very well. It didn't really feel like an hour and a half. There was so much going on. So that's really nice. Yeah.
It's great to hear.
Right. Closing remarks. Marcel, thank you so much for taking time out to speak to us and explain to us how Brian works. And hopefully we'll all find time to, if nothing else, fix typos in the documentation and contribute that way. The lowest barrier of contribution.
That would be great. Yeah, we had several contributions like this, and that's very valuable as well. Yeah, I mean, typos is maybe really the tiniest, but something that happens and that can be very confusing to new users is something like more typos in like example code or these kind of things, like misspelling the argument of something when we are talking about it in the documentation, and it can be very confusing to new users. So it's a very, very useful contribution.
Great. Yeah, if nobody has any other questions, we'll let everybody go on at 30 past, exactly when it's an hour and a half.
That's great.
Yeah, and
we'll have a next session soonish, right?
Yes, so we have a session on NeuroFedora coming on the 16th. We've also just scheduled a session on NeuroLib for the 22nd. And hopefully we'll have a session on Gen soon after, because that's in the queue. In the meantime, if anybody develops any software for neuroscience at all, it doesn't have to be software, it could even be hardware, any development on the computing side, please get in touch with us, because we would love to hear how you develop it, what your plans are, how people can get involved. So yeah, so get in touch with us. The working group is community-based. You don't have to be a researcher or a postdoc or faculty or even a PhD student. You can be anybody who's interested in any sort of computing related to neuroscience, and you're most welcome to the working group, right? The idea is for us to do what we've done today, talk about tools, share ideas, see how different people develop things. Yeah, learn in the process, improve our tools. That's the idea. Okay, with that, thank you everybody for coming. The recordings will be available soon, and I shall see you on 16th, hopefully.
Great.
Thanks, Marcel, in particular. That was great, and I look forward to the next one.
Good stuff. Bye.
Bye, everyone.
Bye, everyone.